Stochastic Emergent Storage, SES, is a novel learning strategy that leverages natural randomness to construct an emergent representation of desired memories. This approach utilizes a vast database of fully random patterns generated by a disordered, self-assembled structure. A set of prototypes, selected based on similarity to the target memory, are used to generate the desired pattern through a weighted sum of their corresponding synaptic matrices. In the photonic domain, SES takes advantage of ultrafast wavefront transformation and parallel operation to demonstrate the convergence of photonics, artificial intelligence, and machine learning. Random transmission matrices, which govern light scattering in a white paint turbid medium, serve as prototypes. This approach addresses the fundamental limit to the number of memories that can be reliably stored using Hebbian-based methods, which recent research has sought to enhance through techniques such as dilution, autopsies, and convex probability flow. The SES method is connected to the concept of emergent archetypes developed in hierarchical clustering, where prototypes represent each cluster. By storing an arbitrary archetype, the authors demonstrate the capability to perform classification at the speed of light, leveraging the vast number of modes excited by mesoscopic diffusion. This approach enables the simultaneous storage of thousands of memories without additional fabrication efforts. Notably, memories can be organized spatially into distinct classes, becoming features within a higher-level categorical optical classification layer. This novel strategy has significant implications for the development of ultrafast, high-capacity memory storage systems. The research introduces a groundbreaking approach to optical computation, harnessing disordered scattering structures for efficient pattern storage and retrieval. This innovative device, referred to as a disordered classifier, leverages the intrinsic patterns of scattering to perform complex tasks such as deep classification. The device's architecture consists of two layers, enabling the comparison of an input pattern with thousands of stored elements. The functionality of the device is based on the interaction between the input pattern and the disordered medium, which is mathematically described by equations 2 and 3. These equations detail the scattering process driven by the transmission matrix, demonstrating the potential for novel optical computing paradigms. This section of the research paper introduces the concept of Photonic Stochastic Hebs storage, SHS, and its application in creating an optical synaptic matrix. SHS is based on the principle that a scattering process generates billions of output modes, each with a unique and random embedded memory pattern xn and the relative optical synaptic matrix V nu. By utilizing a large number of these random optical synaptic matrices as bases, the authors propose a new method to store an arbitrary, user-defined memory in naturally occurring scattering media. The performance of this optical learning approach is demonstrated through the realization of an Hebs dyadic-like optical synaptic matrix from a ZNO scattering layer. The memory pattern stored in the system is X is equals SEIG, JM, lambda T, where SEIG, H, is the operator that finds the eigenvector corresponding to the largest eigenvalue of H and then produces a binary vector with its element sign. The authors report the performance in storage and classification for SHS in Figure 2a and 2b, respectively. However, it is noted that SHS is basis-hungry, requiring a large number of random optical synaptic matrices to successfully construct a memory element. The remainder of the paper focuses on how the performance drastically improves with similarity-enhanced storage, SES. Each optical synaptic matrix contains a memory xn equals SEIG, V nu, and instead of randomly extracting modes, the authors perform a similarity selection. This approach allows for the creation of an optical synaptic matrix that closely resembles the target matrix, thereby enhancing the efficiency of the storage and classification process. The authors introduce a novel approach called Stochastic Emergent Storage, SES, which leverages the mesoscopic laser scattering process to boost performance. SES extracts a set of intrinsic memories, M, whose patterns are closest to the target pattern, phi. These selected memories, xn, can be seen as prototypes of the target archetype, interacting constructively to generate a representation of the memory phi in an emergent fashion. The authors demonstrate the potential of SES in Figure 3, showcasing the stored patterns obtained with SES for different values of M. The results outperform the random selection approach, with an order of magnitude improvement in storage error probability and 3 to 4 orders of magnitude improvement in classification error probability. The system works as a content-addressable memory, identifying the matching memory as the most intense transformed intensity pixel. The authors also propose a new approach to perform higher-ranked categorical classification, employing the cached memories as features, and demonstrate its effectiveness on a repository of 4,500 randomly tilted digits images. Stochastic Emergent Storage, SES, is a novel paradigm for pattern classification that leverages disordered systems to significantly reduce the number of sensors or pixels required for complex pattern recognition. This approach is demonstrated through the use of a photonic classifier, which utilizes an optical setup with a disordered medium and a digital micromirror device, DMD, to classify handwritten digits from the MNIST dataset. The results show high recognition efficiency, even when the number of detecting elements is drastically reduced. For instance, the photonic classifier achieves an accuracy of 95.5% with only 10% of the original number of detecting elements, highlighting the potential of SES to significantly reduce the complexity of pattern recognition systems. The study also explores the implications of SES on understanding biological memory formation processes, providing insights into the connectionist and innate hypotheses. By leveraging Hebbian synaptic matrices and stochastic innate networks, SES introduces a fresh perspective on these hypotheses, suggesting that predetermined random synaptic structures can be combined to generate memory elements in an emergent manner. This novel approach has significant implications for the field of pattern learning and network training, particularly in biological neural networks and neuromorphic computer architectures. The findings presented here open up new avenues for exploring the emergent learning process in these systems, providing valuable insights into the memory formation process in the brain. The SES paradigm offers a promising solution for reducing the complexity of pattern recognition systems while maintaining high recognition efficiency, with potential applications in various fields, including computer vision, robotics, and neuroscience. Here's a refined version of the transcript. Neural networks have been extensively explored in various research papers, with a particular focus on Hopfield networks and their applications. These networks, first introduced by John Hopfield in 1982, are a type of recurrent neural network that can store and retrieve patterns in an associative memory. One of the key advantages of Hopfield networks is their high storage capacity, which enables them to learn and recall multiple patterns efficiently. This is achieved through the use of an energy function, which is minimized during the learning process to ensure that the network converges to a stable state. Research has shown that Hopfield networks can be implemented efficiently using photonic systems, which offer significant advantages in terms of speed and energy consumption compared to traditional electronic systems. This has sparked interest in the development of photonic Hopfield networks for applications such as image recognition and processing. Studies have demonstrated the potential of Hopfield networks in solving complex optimization problems, such as the traveling salesman problem and the knapsack problem. These networks have also been applied to real-world problems, including image denoising and feature extraction. Theoretical analysis has revealed that Hopfield networks can be used to model complex systems, such as biological networks and social networks. This has led to a deeper understanding of the underlying mechanisms of these systems and has paved the way for the development of new models and algorithms. While Hopfield networks have shown great promise, there are still limitations and challenges to be addressed. For instance, the scalability of these networks remains a significant challenge, and further research is needed to overcome this limitation. Additionally, the development of more efficient learning algorithms and the integration of Hopfield networks with other machine learning models are areas that require further exploration. Overall, research on Hopfield networks has opened up new avenues for the development of efficient and scalable neural networks, with potential applications in a wide range of fields. In a novel experiment, light from a coherent source is controlled using a spatial light modulator and transmitted through a disordered medium into mode nu. The transmitted field at nu is described by equation 7, where E nu n represents the field resulting from the laser field from the nth segment, transformed by the transmission matrix element on the sensor nu, and PHNN denotes the phase value from the wavefront modulator. The field at nu can be decomposed into its two components: the field at the segment and transmission matrix element T nu n. The E nu n are Gaussianly distributed complex numbers, as described by equation 9. In the simplified configuration where Phnn takes on values of -1 or +1, the field at nu can be expressed as equation 10. The intensity I nu is calculated as the modulus square of E nu, as shown in equation 11. By expanding and simplifying the equation, it can be expressed as equation 16, which is further generalized for n segments in an arbitrary configuration as equation 17. The argument of the sum in equation 17 can be written in matrix form, defining the optical coupling matrix V nu, a bidiotic matrix that can be rewritten in matricial notation as equation 20. In the presence of modulation, the intensity I nu, phi, can be expressed as equation 21, which associates the pattern array phi to the scalar I nu, a measure of the degree of similitude of phi to the first eigenvector of V nu. In the experiment, each mode nu corresponds to a single sensor, and the one mode per pixel configuration is obtained by properly tuning the optical magnification. The stochastic Hebs storage protocol is employed, where the intensity measured at two modes nu 1 and nu 2 is summed, and considering linearity of the process, it can be expressed as equation 22. Generalizing to an arbitrary number m of modes, the intensity Im is retrieved as equation 23. The authors introduce the concept of an optical operator Jm, which associates a pattern array phi with a scalar Im, representing the degree of similarity between phi and the first eigenvector of Jm. To design an arbitrary optical operator, tailored attenuation coefficients lane element of 0, 1 are introduced, which can be implemented in software or through a modespecific hardware optical attenuator. The transformed intensity with attenuation coefficients is given by equation 25, where Jm lambda is the optical operator with optimized lambda. In the context of storage holographic systems, SHS, the absorption coefficients lambda are free parameters that enable the design of an arbitrary optical operator Jm, lambda. The authors demonstrate how to replicate a dyadic matrix constructed using Hebs' rule by selecting lambda to minimize the function f, m, lambda, in equation 26, which represents the distance between the optical operator Jm, lambda and the target operator t. The resulting optimized optical operator is denoted as Jm, lambda t, and the corresponding transformed intensity is given by equation 27. The authors highlight that the effectiveness of this approach depends on the number of free parameters lambda compared to the constraints, which are the number of independent elements that need to be tailored on T. In the case of a symmetric matrix T, the number of constraints is pi equals n, n1, 2, where n is the size of the matrix. The authors show that when m greater than pi, the number of free parameters is comparable to the constraints, and the target operator T can be replicated almost identically. The authors also discuss the storage error probability, which represents the effectiveness of the storage process. This is calculated as the ratio of the number of error pixels in the stored pattern image to the total number of pixels. A lower storage error probability indicates better storage performance. Furthermore, the authors introduce the concept of classification error probability, which is used to evaluate the classification performance of the optical operator Jm, lambda t. The transformed intensity is experimentally measured for a repository of 5,000 patterns, and a pattern is considered recognized if the transformed intensity is above a certain threshold. The classification error probability is then calculated as the ratio of the number of wrongly identified patterns to the total number of patterns. The stochastic emergent storage (SES) protocol leverages the intrinsic random patterns present in optical coupling matrices to create memories. This is achieved through a multi-step strategy that begins with measuring transmission matrices from a large set of modes using the complete couplings mapping method, CCMM. These matrices are then stored in a computer memory, forming a repository of starting random structures. Next, the first eigenvector xn is computationally found for each measured matrix V nu. A target memory pattern phi asterisk operator is designed by the user, along with specifying the number of modes m asterisk operator to be employed. The similarity between the target pattern and all eigenvectors in the repository is computed as the dot product of normalized vectors phi asterisk operator and xn, resulting in a similarity score S nu. The repository is then similarity decimated to the set M asterisk operator, selecting the modes with the highest S nu values. Following the selection of the repository of modes, the attenuation coefficients lambda are optimized using a Monte Carlo algorithm. The lambda values are chosen from a range of 16 values, corresponding to 4 bits of absorption. The optimization process involves modifying a single lane at each step and accepting the change if the eigenvector similarity function f asterisk operator, lambda, phi asterisk operator, m asterisk operator, decreases. This function is defined as the dot product of the first eigenvector of the optical operator jm asterisk operator, lambda, and the target pattern phi asterisk operator. The experimental setup used for measuring the optical synaptic matrices V nu and performing classification tasks is described. It includes a single-mode laser, a digital micromirror device, DMD, and a detection camera. The DMD is used to modulate the light rays, which are then scrambled by a diffusive, multiple scattering medium. The back layer of the disordered structure is imaged onto the detection camera, allowing for the measurement of transmission matrices. The experimental setup is sketched in Figure 5, illustrating the naming conventions for the input modes, segments, and detectors, output modes. The setup operates in a one-mode per pixel configuration, enabling the measurement of transmission matrices with high accuracy. The methodology employed to obtain the superpixel method involves a 2.66 mm aperture iris in front of the DMD. It involves equations for calculating intensity when 2 DMD mirrors are activated and when a single segment is activated. The process requires 3 intensity measurements to determine one element of the optical synaptic matrix. For reconstructing the full matrix with n equals 256, 32,896 measurements are needed, which can be achieved in 5 minutes using the DMD camera setup. The data is organized into a 32,896 by 256 by 256 matrix, with limitations imposed by the random access memory size of the computing workstation.